Hello, this is the first problem that we'll use calculating flow with different methods. The example I'll give today is using Darcy-Weisbach, but the same process applies for Hazen Williams and Manning, which is the problem that you have to complete the second problem in that handout. So let's read the problem. Determine the flow rate of water, and here we have 20 degrees Celsius. That will cause a pressure drop. Here, important, this number of 17,250 newtons per square meter in a 350-meter horizontal cast iron pipe with a diameter of 60 centimeters. Assume that minor losses are negligible, and you can assume turbulent flow. Of course, your assumptions always have to be proven. So let's write the information that we have. We have a temperature of 20 degrees Celsius, and of course, in Darcy-Weisbach, this is important because this will affect the viscosity of the water. And we have a pressure drop of 17,250 newtons per square meter. The length of the pipe is 350 meters. It's a cast iron pipe, which will tell us the roughness. The diameter is 60 centimeter or zero point 0.6 meters, and minor losses are negligible. Always, you need to write all the energy equations first and foremost. So we have V1 plus V1 squared over 2G plus V1 equals V2 over gamma 2 plus V2 squared over 2G plus C2 plus HL. Now, here all the losses are just for friction, so I'll just put here friction. First thing is the diameter of the pipe does not change. I have the same velocity. It's a horizontal pipe, so this doesn't change. I have P1 over gamma 1 equals P2 over gamma 2 plus HF. But of course, I know that P1 minus P2, what is that? The gamma does not change, equals HF. So the difference in pressure is 17,250 newtons per square meter, and I divide that by the specific weight, and this is 9,790 newtons per cubic meter, so the losses here are 1.76 meters. So what we have in summary, HF, which is 1.76 meters, these are the losses, and I'm using here, as I said, Darcy-Weisbach, so this is equal to FLD V squared over 2G. Now we're using this to calculate the flow rate, and for the flow rate then we need to have the volume. So this is our unknown, and we have the information on the length and the information on the diameter. We have this, so we'll need to get the friction factor. In order to get the friction factor using Darcy, you need the relative roughness, and also generally you need the Reynolds number, but we're assuming is turbulent. So let's do the calculations for the epsilon over the diameter. So it's a cast iron, so here is my epsilon. So epsilon over d would be 0.26 divided. Oh, and then the units are important because this is 0.26. This is in millimeters. and then I divided by, I have 60 centimeters, so I have to make the conversion. So I have 0.26 times 10 to the minus 1 divided by 60. So everything is centimeters over centimeters, and then the number I get is 0.0004033. So 0.004 is here. This is 0.006. I have 3 zeros, sorry. I have 0.0 is between this and this. So it's going to be more or less, and if I'm assuming turbulent, look at this value here, and I just go straight, and something like 0.017 is my friction factor. So let me go to this here. So it's 0.017. Okay. So now I calculate the velocity. So I solve for the velocity because everything else is unknown, and take a break from the video and make sure that you can do the calculation, and the velocity that I obtain is 1.87 meters per second. One thing you should always do is double check your calculations, because see, now you can calculate the Reynolds number because you have the velocity, and see the velocity times the diameter over the kinematic viscosity. So I have a velocity of 1.87 meters per second, diameter 0.6 meters, and at the temperature, the viscosity, the kinematic is 1 times 10 to the minus 6 meters squared over second. So my Reynolds number is 1.12 times 10 to the 6, and it's in the turbulent range. Okay, so it's here to the 7 to the 6, so it's more or less in this range. So the presumption was not very difficult. So I hope this helps, and good luck with the other problem.